Let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1207. Let's see here. Okay, it's working. All right, let's jump into it. There we go. Right. So let's talk about what we spoke about last time. We derived some Taylor series. I think that's probably the previous lecture where we actually defined what that was. So last time we spoke about something called a Taylor series. Remember, a Taylor series is just a series that has this formula. The Maclaurin series is just a Taylor series centered at 0. However, this is a series that we can generate from a function, given a function f of x that is infinitely differentiable. We can just keep taking derivatives. We can use the derivatives of the function evaluated at a point called a center point to develop a kind of series. And in fact, it's a kind of power series. So it will generate a power series using a function. And sometimes the idea being is that this series will actually describe the function very well in such a way that you can even replace the function by the series. And in some cases, this might look like you're replacing it with something more complicated, but actually it makes things a lot simpler. And sometimes it's actually preferable to think of things in terms of their series definition as opposed to whatever they were defined as before. So there's this thing called Taylor series that we can generate from a function. And we actually did some of that, actually directly computing the Taylor series of a function using derivatives. So we did an example for e to the x. We keep taking derivatives over and over. The idea is to find a general formula in terms of n that describes the coefficients that you can then plug into that formula in the box. And of course, every time you have a series, you'd want to know where it works. So you can do the ratio test to figure out on what interval would this series actually do what you think it would do. So we also found it for cosine, and that was a series. We just claimed that it was a very similar process for the sine of x. And we ultimately developed these 4 series, which at this point, these are the series, these are the functions whose power series or Maclaurin series, which is just a special case of a Taylor series that I expect you to know by heart. These are just direct definitions. And a lot of people think of these functions as these series because it's actually a better way to think about them most of the time. So then we actually saw some applications of Taylor series, did a lot of cool things, found a lot of cool equations, learned how to expand a sum under a radical, learned a different way to compute limits, learned how to write functions at constants as infinite sums, found that we could derive a lot of formulas that we knew before, a lot of derivative formulas, and a lot of trig formulas actually fall out of all of this very easily. And we learned how we can compute very difficult integrals that are in some sense impossible for us to compute before. Now we can compute them. The only difference is the answers come to us as infinite series. And there are times when we can actually write down a function that describes that series in any way other than the series, or maybe some shorthand notation that glosses over the whole notation. We saw that we can actually get pretty good approximations to these series. So in some ways, it's kind of better than having the real nice answer, because we can't use the real nice answer anyway. We can only use approximations in real life. And so with this, we can actually get the answer to within any degree of accuracy we want. And we did some examples where we did that for alternating series, because the answer of our integrals were alternating series. So we could use the alternating series approximation theorem to say how close we are to the answer and say whether or not we're bigger or smaller than the actual answer. Then we started making comments about when a Taylor series actually describes the function that generates it. So this formula, you might think, oh, if I take any function and I start differentiating it over and over and constructing the series, then all right, I can use these interchangeably. That isn't exactly true. There is a difference between being infinitely differentiable and being what we call, well, analytic would be the phrase for it. And that's kind of a term that you'd hear in a complex analysis course. So they talk about something is analytic. Basically, it means that a function is called analytic if it can be described by a power series, in the sense that you can interchange one or the other and no one will know the difference. Not all functions that are infinitely differentiable are analytic. And so we want to know, when we do a construction like this, when is it actually useful? And it turns out we actually have an exact criteria for when that is the case. Yeah, which was here. So we can break up a Taylor series into two parts, the nth degree Taylor polynomial and the remainder term. And it turns out if the remainder term approaches 0 as n approaches infinity, then the function and the Taylor series that we construct from the function will be one and the same. Otherwise, they are not considered to be the same. It means that there will be differences between the two, and the Taylor series can actually describe something else. So what I wanted to do last time, which I just kind of just called it quits, was to actually go through some examples of what happens when finding Taylor series goes wrong. So I just wanted to give you some examples. Hopefully they're not some simple examples for when this process actually doesn't work and the kind of problems that you can run into. But when it does work, it's a beautiful thing. I even showed you guys some animations of that last time, of like seeing a polynomial fit to a function. That's essentially what a Taylor series does. And if you stop it at any finite point, it's never going to fit correctly because something is going to be off. But if you keep going, it'll fit the function exactly. And so the infinite series can describe the function in its entirety. But there are times when this doesn't actually work out. So I just want to give you guys some examples. So for example, here's one. Sometimes you can't find a Taylor series, at least at a certain point, because you simply can't finish the process for finding a Taylor series. So for example, if I wanted to look at the function, the absolute value of x cubed, and I wanted to find a Maclaurin series for this, it turns out that I actually could not. And you can see this directly by just going through some computations. It turns out that the derivative here, and this is something that you'd have to work out in detail, but I'm just going to skip to the answer. The derivative here is going to be 3 absolute value of x squared, right? Now, you define the absolute value by the piecewise function, take the derivative of each piece and stick it together, and you'd realize, oh, you'd get it same as the absolute value of x squared, which, again, you can differentiate that. And you get 6 times the absolute value of x. Now, obviously, this means the 0th derivative evaluated at 0 is 0. This would mean the first derivative evaluated at 0 is also 0. This would mean the second derivative evaluated at 0 is 0. And what is the third derivative? Turns out, does not exist. So the absolute value function is one of those functions that we saw in Calc 1, doesn't actually have a derivative at 0. We know that derivatives cannot exist where we have sharp corners, discontinuities, or vertical tangent lines. So yeah, the process stops. Like if I don't have a third derivative, I can't find a fourth or a fifth or a sixth or a seventh. So the process just stops, it terminates. And even what we have so far is just a bunch of zeros. So if I were to say, all right, let's just look at it like a finite series, I still get a series of zeros. It doesn't describe the function absolute value of x cubed, right? So yeah, unable to find f to the n of 0 for n greater than or equal to 3. So f does not have a Maclaurin series. All right, so this is just an example. Sometimes you can want to create a Taylor series, but the function doesn't behave at the point that you care about. Some functions will behave at any point. But a function like that, I think, would be very difficult to explain at the Calc 2 level, I think. Something like the Dirichlet function or something like that would give such issues. But yeah, here's one that at 0, it gives issues, and you can't actually find a Maclaurin series. So here's another one. So let's say we can construct a function where the derivative is always defined of all orders at 0, and we define it to be this. And this definition of a function might seem like a strange definition. I don't think at this point in your lives, up to Calc 2, you'd see functions defined this way, but you can define a function this way. And it's kind of like me defining a function, which this isn't quite the error function. I guess this is like define a radical 2 pi times f of x to be this. This is something that you have seen before. In Calc 1, towards the end of Calc 1, you've seen us define functions as integrals. And you can realize that it's actually the same as defining a function whose derivative is anything. So I can make a definition for a function like this. And notice that this is equivalent to me defining the function as f such that f prime would be e to the minus x squared, right? So that could be defining a function in terms of what its derivative would be is a bona fide definition of a function, right? We can define functions in terms of integrals. We can also define them in terms of derivatives. But to not get too complicated with the examples, I'm defining a function based on what its derivative will do. And you'll actually notice that this derivative here actually has, if I were to plug this in, so the Mach series for f of x would be just a series, n goes from 0 to infinity, of n factorial squared over n factorial times x to the n. Of course, this would mean this is just a series of n factorial x to the n. So it's just a infinite polynomial where the nth coefficient is given by the nth factorial. And it turns out, ratio tests would show this diverges unless your x equals 0. So in other words, your Taylor series only works literally at the origin, like right here. Which, I mean, that's kind of useless, right? So you'd expect this function f of x to work everywhere because you can find its derivative everywhere. But the Taylor series will only work specifically at one point, which doesn't even, it's not useful at all. There are more numbers we'd want to care about than at 0. And at 0, the output here would just be 1. I mean, okay, I have a function that's 1 at the origin, and it's not defined anywhere else. Okay, you just defined a point, not very useful. So again, that's a situation where the Taylor series, even if you could find it, doesn't help. Here's a third example. So in the first example, you couldn't even find a Taylor series to begin with because you don't have all the derivatives. But it's possible to have all the derivatives and the series still doesn't work or doesn't describe what the function would look like. Here's one where it doesn't really have something like this. It'll actually work everywhere, not just as a single point, and you will be able to find all derivatives and evaluate them, but it still doesn't work. And it's this piecewise function here. It's actually a very famous example. And it turns out, I'm not going to do it for you because, I mean, these are just some examples, but you can actually show that f to the nth derivative evaluated at 0 is 0 for all n. And this would actually obviously mean the Maclaurin series would just be a set 0 times x to the n, which is just the series of 0 plus 0 plus 0. So below is a picture of this function, and the blue is the picture of the Taylor series of this function. So you can actually compute the Taylor series, but it just gives you a constant function of 0. So this is the graph of the Taylor series. So the Taylor series is an actual function that exists all the time. It's close to this guy when you're close to 0, but obviously outside of that window, it's not a good approximation at all. And this is the graph of f of x. So this is a function where you can keep taking derivatives, and you can create a Taylor series from it, but you get this kind of Taylor series that's always 0, and which it works. It's just that it gives you the function, it's equivalent to the function y equals 0, and that obviously doesn't describe the red function. So you can find a Taylor series and everything seems to work until you go back and you check it with the original function and you realize these two don't actually behave the same. And this one, it's not as dramatic as the last one, but it's the same sort of idea. If you were to check in the ratio test, you'd see eventually for certain x values, the series won't converge. The coefficients of the function will diverge faster than the Taylor series will converge to the function. And so that's what happens. The Taylor series could keep pace with the function for a while, but eventually the function's derivatives get so big that the Taylor series can't keep up. It just kind of gives up. It's kind of something that you'll see. So I just wanted to give some examples of, like the idea that a Taylor series, it seems magical by a lot of the applications that I was talking about yesterday, but they don't always work out. And so it turns out that we actually know when it would work out. And that's something that I would expect you to know. I thought I asterisked this before. Okay. So this is just something I expect you to know conceptually, at least. I probably won't ask you any direct questions like, oh, do these calculations and then figure out what's wrong. Like I wouldn't ask you that, but I'll just ask you probably direct questions about would a Taylor series always exist, or what are the conditions that we need, things of that sort. You should just have an idea. And so that essentially wraps up the entire discussion about series. That's all I really wanted to do about series. So you know what series are, you know how to talk about when they converge, what it means for them to converge, how to test that they converge, how to test whether they converge absolutely or conditionally, or whether they diverge. You also know how to use them to do stuff like compute very difficult integrals or simplify other things, compute limits. You also know what certain important functions, what their Taylor series are, or Maclaurin series. Where did I put this? These guys, expect you to know that. And yeah, just generally how when a Taylor series would work, when it would not work, and just knowing that, yeah, it's magical when it does get to work, but it doesn't have to work, and so you kind of have to be careful with certain things. So now we are actually going to go into a whole new topic, or to be more specific, we're going to go into a whole new phase of the class. So I mentioned that, let's see, let me find it here. Well, I can show you. So we're going to go back to our table of topics, see where we are, what we have left. So we've completed phase 1 and phase 2, what's in the 1 circle and what's in the 2 circle. So now we're actually going to move on to the 3 circle. And at this point, I don't even actually care about everything in the 3 circle. So the most important things for me, and I might rush through the other things, or I might just like forget about them altogether. But the most important things I think we should know is topic 16, 18, 19, and 21. And 21, I'm really only going to talk about sketching them, really. So we won't need to know about conic sections in complete detail, but especially in the future and for future classes, especially if any of you are going on to Calculus 3, knowing how to sketch conic sections will be very useful. 15, 17, I mean, I might talk about some things in 20, but I wouldn't be too worried if we don't even get to those. It's the sort of thing where it's like, it's cool, you know, and it would be fun doing them, but it's like you're never gonna actually revisit this in your entire life. Like I've never done these things outside of a Calc 2 class specifically. It's just, yeah, they're not very, it's I don't want to say they're completely useless and no one's ever cared about them, but it's like we're past that time, you know. It's kind of like if you were to sign up for a mechanics course and they start teaching you about horses and buggies, you're going to be like, yeah, we have cars now, so you know, why are we spending time on this? That's kind of like what it is. So in Calculus 3, you're going to learn about very sophisticated ways to find volumes and areas, and it just makes finding volumes in other ways like a waste of time. Like why would you even do that? So yeah. So for now, we're going to start phase 3. And there are, as you can see, 4 important topics in phase 3 and 3. If we have time, we'll get there. But that being said, let's move on. So we're going to phase 3, where we're going to talk about parametric curves and polar coordinates. And there's another part to phase 3 where we deal with the conic sections and maybe some of those throwaway topics. It depends on how things go. We're playing it by ear. But yeah, so I want to introduce maybe a new concept for some of you, although not that new, because as I'm gonna mention an example that you guys have all seen before, and you're gonna realize that this isn't actually that new. I just want to generalize some concepts, and we want to know how to think in a different way because it will be useful again in the future. The way we've been doing things worked up till now because all your life you've been living in the 2D plane. There comes a point where you want to go 3 dimensions and higher. Calc 3 starts talking about 3 dimensions, and higher is just, it's a very natural thing to do. So a lot of applications in mathematics, you're working in many dimensions. There are lots of applications in mathematics where you want to work in an infinite number of dimensions, whatever that would mean. So when it comes to that, knowing about parametric equations and vectors and things like vector functions becomes very important. And the idea behind parametric curves and their calculus becomes very important as well. So, but we don't need to worry about that in the future. Right now, I just want you to know what a parametric curve is, how to deal with them, what polar coordinates are, and how to deal with them. And so, yeah, let's actually jump into it. So we're kind of going to do 10.1 and 10.2 kind of match together, just one continuous flow, because they're really talking about the same thing. Yeah. So we're actually used to seeing curves in the XY plane in this form, like a function of x and y equals a constant, like y equals x cubed, or x squared plus y squared equals 4. These are all equations that hopefully seem somewhat familiar to us. So we know that the first one is, you know, it's a guy that looks like this. Yeah, that's y equals x cubed. And we know that this one is just the equation of a circle of radius 2. which technically is not a function, but so it would pass through here at 2, minus 2, minus 2, 2, right? So these are all things that we've seen before, and we can write down an equation for them, right? So y equals x cubed, x squared plus y squared equals 4. We understand that means these are functions, and this is what their picture would look like in the Cartesian plane. So here's the thing though. Sometimes you actually want to describe a function in a different way. Sometimes we want to think of a function in this way, where we actually break down each coordinate and we think of those coordinates as separate things that are coming together to create the one thing that is the function, right? So you can think of the x coordinate independently moving on its own, doing its thing, the y coordinate independently moving on its own, doing its thing, and when you put them together, you get a function. But sometimes we want to decouple these two. We want to look at them as functions in their own right. Once you do this, you say you're talking about them as parametric functions, right? So there's another parameter that you invent, and you pretend that those two guys are functions of that new parameter. And it's called a parameter, hence this the phrase parametric functions. And this is actually something that you've seen before. So trigonometry is one place that you've seen this before. Remember, how did trig actually come about, right? So we've seen this before. Think trigonometry. You're like, what are you talking about, Jhevon? Remember what trigonometry was? We looked at the unit circle, right? Going circle of radius 1 centered at the origin. And what we did was we picked a coordinate on the unit circle. And what we wanted to do is we wanted to look what the x coordinate and y coordinate were doing separately. So we thought of an angle subtended by the positive x-axis. And what we said was, let's invent a function that's going to tell us what the x is doing and what the y is doing based on what this angle is. And these two functions were the cosine function and the sine function, right? So cosine of 0 is 1 because when the angle is 0, the x coordinate is 1. And sine of 0 is 0 because when the angle is 0, the y coordinate is 0, right? Cosine of pi over 2 is 0 because when the angle is pi over 2, the x coordinate is 0. And sine of pi over 2 is 1 because when the angle is pi over 2, the y value is 1, right? So we are actually looking at the x and y as separate entities, right? And we create two functions on their own. So when we put them together, you get a circle, but separately, the x is behaving like a whole other curve. It's behaving like this curve. And the y is behaving like a whole other curve. It's behaving like this curve, right? So we have these two separate functions on their own that when we put them together, they create a different function. And we think of this new function that they create as like x squared plus y squared equals 1. But separately, they're their own functions, right? We can think of the x and the y as acting by themselves. And sometimes to denote this idea, we use a whole other variable. So now we have the variable theta that would describe to us what the x and y are doing separately. And so when you actually describe that, right? So when you go into a circle and you say, you know, your x equals cosine theta and your y equals sine theta, right? Your theta is the angle, right? But in this case, it would be called a parameter, right? And these guys would be called parametric equations. Right? Because they arise out of us trying to define this new parameter to measure the coordinates separately in terms of, right? So that's the idea, right? So we can do this on the unit circle and we got trigonometry. And look at what we get from trigonometry. There's a whole list of functions and uses that come out of trigonometry, all by us considering. Let's see what happens if we think of the x and y as separate. The entire subject of trigonometry was born just from that one idea. in the same way, we want to generalize this. We don't just want to trap ourselves to a unit circle. We want to be able to do this in general. What if we can go anywhere and just think of each coordinate as individually acting on its own, use functions to describe each coordinate? What could we do with that? And what would the math in that kind of way look like? That's the idea behind this chapter. Okay? So that leads us to our definition. Suppose x and y are defined in terms of some new functions, and there's a new variable called t, called a parameter. Then the equations x equals x of t, y equals y of t are called parametric equations. And the parametric curve is me describing to you what the x is doing, what the y is doing, and what the limits on the parameter are. So for example, you can trace out a full circle by me saying, something like theta goes between 0 and 2 pi, right? And that will trace out this full curve. Now, of course, I could let theta go beyond that, but then I would just be retracing the same curve, right? So there's always this part of the system that sort of tells you what your new input variable or what your parameter is allowed, the values that it is allowed to take on. Okay. Now, to have some new terminology, we call the initial point to be what the coordinate values are at the first parameter value, t. So when t equals a, the x and y will have a certain value. And when t equals b, that looks like a typo here. This should be an a. Let me fix it. Me typing too fast. Okay, so that's the initial point or the starting point. And then you have so another way, this is starting point. No one calls it starting point though, but that's what it is. And then there's the terminal or the final point, and that describes exactly what the curve is doing between these two coordinates. It is also possible to let the parameter be unrestricted. And so you can write something like the parameter goes from -infinity to infinity. So it can take on any number it wants, or you can say t is in R, and that would be describing the same thing. Okay. So now let's actually look at doing things like sketching a parametric curve, right? So we don't just want to be able to talk about them, but we want to be able to actually get pictures from them, because as we know, knowing how to sketch pictures would help us with mathematics a lot. So I do want to mention how to actually sketch them. There's also a warning here that parametrizations aren't unique, and I'll probably show you some examples of that later. Okay. But for now, let's actually do an example, right? So we know what parametric curves are. Now let's actually see how to go about sketching them. Right, so look here, we have a parametric curve described like this, right? So the x is equal to 2 minus t, and the y is equal to 3 plus 2t. And your t goes from 0 to 1. Now, there are two ways to actually go about sketching these. And there's going to come a point where you're not really going to need either of these ways to figure things out. Like by the time you get into a Calc 3 course, you're going to get to a point where you can just think in terms of parametric curves. But for now, we're going to use crutches a little bit. And we're going to take baby steps to figure out how do we go from a parametric curve to the XY plane like we're used to, right? So that's what we're doing. And so one method is to plot points. Okay. So we've described what the X is doing and what the Y is doing. So it turns out we can actually plot points to figure out what's going on. So for example, I can say, all right, my X, my Y, or we start with the T because T is telling X and Y what to do. So T will take on some value, X will take on some value, and Y will take on some value. Right? So I can put in the starting point and the ending point, those are usually nice things to put in. And I would actually use these equations to evaluate, right? So when t equals 0, clearly x will be 2. And when t equals 0, y will be 3. And notice that what this means is this is helping me find the initial point. It's actually the coordinate 2, 3, right? So that coordinate will actually be on the graph. Similarly, for the final point, I can plug in t equals 1, and you'd notice that x would be 1. And if I plug in t equals 1, my y would be 5. And that's like me finding the final point. One comma 5. So I know this is a curve that goes from the point 2, 3 to the point 1, 5. So I know the two endpoints. Now, what you would generally want to do is you want to plot some intermediate points to kind of see what's going on. It turns out here we can get away with only plotting one other point, because we know that if, or at least I'm telling you now, that when x and y are linear, then when you put them together, you also get something that's linear. You get something that looks like a line. And you can plot a bunch of points and see that this would have to be the case. You'd see that the slope between any 2 points is a constant. We're going to talk about slopes of parametric curves later on, by the way. And you'd know that this is a line based on that. But for now, you can take my word for it. When x and y are linear, you will get a line. So let's put in a halfway point. Let's actually put in a half. When t equals a half, I go to the x, I plug that in. 2 minus a half is 1.5. So that's 0/2. And when t equals a half, I go to the y, plug that in, I get y equals 4. So there is a coordinate 3/2, 4. So I can go and I can plug in a bunch of points. Now from this, I'll actually know how to graph what this would look like in the old familiar XY plane. I know when 1, 1.5, 2. I know at 1, when I'm at 1, the y output is 5. So this is y, this is x. So give me this. I know when I'm 2, the output is 3. Not drawn to scale, obviously. And when it's 3/2, the output is 4. So you can actually get, well, this should be a straight line. I don't, Brian did, I should do that. Same. So that would be a picture. This is actually just a straight line segment going from the coordinate 2, 3 to the coordinate 1, 5. Here's another thing that parametric equations also help us with, because this will be important. And some of you can imagine, for example, that you start using math to study things like physics, and things like direction would be important. So sometimes what's important is not just the path that you go along, but what direction you're traveling around that path, right? So this could make a difference in if you're studying circuits or something like that, for example, or electromagnetism, and you're worried about, modeling the direction in which an electric current is flowing. Notice that there's a natural direction induced by us looking at something as a parametric curve. There's a notion of an initial point and a final point. So here we have the initial point, and here we have the final point. And so you kind of get this idea that we're moving in this direction. We're going from here 2, 3, and we're moving towards 1, 5, and we're doing so in a linear fashion. So that's an additional let's call it connotation. of parametric curves is direction. Right? Now, when someone writes down, like y equals x cubed, there's nothing about direction really implicit in that. In fact, they call when you write down a function like this, it's called the scalar form of the function because it only cares about magnitude. It just tells you when x is this big, your y is this big. That's all it tells you. There's no notion of, oh, we're moving in this particular direction. But with parametric curves, the notion of direction is actually built in. When I describe to you something in terms of a parametric curve, there is an idea that, oh, here's a curve, but I'm actually moving in a certain direction along that curve. And we'll actually look at that in more detail later. By the way, this actually is true for the circle, right? When you measure x as cosine and y as sine, and you let theta increase in the natural increasing way, theta becomes more and more positive, you actually move in the counterclockwise direction. You actually would move around the circle like here. You notice that when theta equals 0, you're at the coordinate 1, 0. When theta equals pi over 2, suddenly you're at the coordinate 0, 1. Theta equals pi, you're at the coordinate -1, 0. When theta equals 3 pi over 2, you're at the coordinate -1, 0, 0, -1. And so on. So there's actually a natural direction that is induced once you start describing the x and y directly, separately. So that's another notion that's very important with parametric curves, right? And so that's how we would actually go about describing it in the picture, right? So if I give you a parametric set of curves and I ask you, hey, draw a picture of this, sketch a graph of this parametric curve, this is one way you'd go about doing it. I would say it's probably not the best way to go about doing plotting points, especially for something that it's just not a good way to graph things. Hopefully you guys have seen that already. I mean, you learned to plot points a long time ago to sketch curves, but when you're in a calculus class and your professor tells you sketch y equals x squared, you don't plot points. You just know what that looks like, right? And you know that if he asks you to sketch x minus 1 all squared, oh, I just take a y equals x squared and I shift it 1 unit to the right. Like you have these ideas of how to get curves without actually plotting a bunch of points, because plotting points is actually very inefficient for a human being to do. For a computer, that's how things would get done. But for a human being, like a curve can be have so many twists and turns in it just by plotting points, you'll never actually get them all, right? So you can have a curve that's doing this, blah, 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 blah. But you decide, oh, I'm going to plot points. And then you plot this point, and you plot this point, and then you plot this point, and then you plot this point, then you plot this point, and you're like, oh, the curve must look like this. No, it doesn't, right? You just didn't plot enough points to get it very accurate. And so it's super easy to not be accurate by plotting points. But for super simple graphs, if you're totally clueless, you can kind of take the plotting points route. But plotting points isn't a good way to graph in general. Like there's a reason why that fell out of favor after a while. And we teach you about transformations of graphs and things like that. Because plotting points, imagine trying to plot a sine function with a bunch of points, right? You think it looks like a sawtooth or something. You wouldn't get the full picture. Another way is to actually bring it back to a place that you understand. So you can bring it away from a parametric curve into a regular scalar curve. So this method is called eliminating the parameter. It's usually done via something like substitution. So this means removing the parameter, usually through substitution. To go from a parametric equation to a scalar one. Okay. So let's go back to our guy right here. So we had x was equal to 2 minus t, or y was equal to 3 plus 2t. T was going between 0 and 1. Right, so this was our curve. So notice what we can do here is from the first equation, we can actually solve for t. We get t equals 2 minus x. And then what we can do is we can plug into the second equation. So that's where the substitution comes from. So we know that our y is 3 plus 2t. So here our y would be 3 plus 2 times 2 minus x. And so this is 3 plus 4 minus 2x, or in other words, your y is equal to 7 minus 2x. And so now you can actually go and you can plot this guy, right? So we know what 7 minus 2x is going to look like. It's just going to be it's going to be a line like this. Right? It's going to have y-intercept 7. And when y equals 0, your x is going to be 7 over 2. So this will go cut across here at 7 over 2. So like 3.5. Now that's not the exact curve. We need to find the endpoints. So when t equals 0, we know that our x equals 2, y equals 3. And when t equals 1, we know that our x equals 1, y equals 5. And so you can get this point here, which is the final point, which we know happened at 5, 1. And you can get another point, say here, which is the initial point, which we know happens at 2, 3. And so the parametric curve, the actual curve, is just this part of the line segment here, moving in that direction. So this is the parametric curve here. Right? But to get that picture, I first converted it to a familiar kind of picture, a familiar kind of equation, y equals mx plus b, right? Y equals 7 minus 2x. I can sketch that in general, but remember I have to pay attention to the limits given to me by the parametric curve, which says t goes from 0 to 1, which means we start and end somewhere, whereas the line goes on forever in both directions. Okay. So the idea is if we did have am I going to be able to do this? Okay. Actually, if we had x equals 2 minus t, y equals 3 plus 2t, and t goes from minus infinity to infinity, then the parametric curve would be the entire line, right? Be the whole thing. It would still be moving in this direction. Right, so that's two ways to find a parametric curve. But later on we're gonna to actually sketch one or have some sort of visual representation for what a parametric curve is. Later on, I'm going to give you some rules of thumbs where you can kind of know based on like what the equations look like, what kind of curve it's describing. And generally speaking, figuring out that a parametric curve you're looking at is a straight line is pretty easy because each component would look like a straight line. Each component would look like a y equals mx plus b kind of thing, a constant plus a constant times a parameter. But if you have something a little different, you can plot some points to kind of figure out generally what it's doing, or you can eliminate the parameter altogether. Just do a bunch of substitutions until you get an equation in a familiar form that you can sketch. And then you kind of find out if there are endpoints where they would be. If there are no endpoints, it means it'll just keep going in whatever pattern that you've described. So here's another one. Any questions so far, by the way, on what a parametric curve is or how we graph one?
I mean, I guess I just have a general question about how things are going to be structured for the next exam. Like, is it going to be weighted equally between the previous section and this section?
It'll probably mostly be on series. So maybe it'll something like 2/3 series, 1/3 this other stuff. Where series also includes the going all the way up to Taylor series, like everything we did with series.
Dope, thank you.
The bulk of it. But it's a non-trivial part will be this stuff. Okay, let's continue. Let's say we want to sketch this, and notice that this has no restriction. X equals 2t plus 1, y equals t squared, and we want t's to go from negative infinity to infinity. So I'm going to do the second method here because plotting points is generally something I would avoid if possible. So we can start off with, well, we know that x equals 2t plus 1. This would mean that I could solve for t. That would be x minus 1 all over 2. And this would mean y equals t squared. This means this would be x minus 1 over 2 all squared. So this would mean my y would be a quarter x minus 1 squared. So that I would be able to describe, that's just a quadratic. Right? X minus 1 squared. I know the scalar is just going to stretch it vertically with a parabola. You're not really going to notice that on the picture. You're just going to know from the coordinates. So I know that this will go through 1, and I know that this happens when x is 0, and you know, so when x is 0, your y is actually equal to 1/4. So this goes through 1/4. I can also just make up my own initial point. just to kind of figure out what direction we're going in. So for direction. We'll do a makeup initial. Say just starting from t equals 0, just because. And then make up final point. T equals 1. Now when t equals 0, go to x, you'd get x equals 1. Y would be equal to, well, y would be 0. Then if t equals 1, you go to x, you get x equals 3. And y would be 1, it looks like. So we have like a 1, 0. This is like my initial point. What's a fake initial point, right? And then I would have 3, 1. So something like here. 3, 1. This is the final point. Well, of course, it's fake. I just made it up to just kind of direction. So we're moving in this direction. So it means I can think of this entire curve as traveling in that direction. So not only do I have a parabola, but I have an idea of a parabola where I'm moving to the right on that parabola. Right, and that's me using the eliminating the parameter idea. Now, there are some general things that we can talk about. Right. There are certain properties that you can see. Like if your x and y are linear, the parametric curve is also linear. If your x is linear and the y is quadratic, your parametric curve will be a parabola. This can also vice versa. Right, so if your y was linear and your x is a quadratic, it's also quadratic, but it will be a sideways one, a sideways parabola. If your x is a linear function of cosine and your y is a linear function of sine, that gives you a circle or an ellipse based on the coefficients of the sine and cosine. So there are all sorts of patterns that we can get used to. And the more you practice with, more you work with parametric curves, the more you're going to realize these certain patterns. You'll be able to see a parametric curve and you can kind of look at it and know, oh, that's a line, or that's a parabola. Oh, that's a circle, that's an ellipse, right? And we're actually going to describe some of these in greater detail. So like the circles and ellipses, I'm going to show you exactly what those would look like when we get back. So we're going to take a break. We're on the hour now, so we'll take 5 minutes and I'll see you guys back here in a bit. All right, so let's continue. So we found what parametric curves are. Just when we think of each coordinate as being individual functions on their own in terms of some other variable, this variable is called a parameter. And we can sketch them by plotting points based on the values that each coordinate has given some value of the parameter, or we can try to eliminate the parameter altogether and rewrite the function in terms of our old variables. Now let's actually go on to talk about some standard parameterizations. So I did mention earlier that there's no unique way to do a parameterization. You can have the same curve parameterized in infinitely many different ways, just by changing how you want the input variable to behave and what functions of the coordinates that you want to choose. And you can actually do this in multiple ways. So it's not like there's any one way to parameterize something or write it in terms of parametric equations. So that's some vocabulary there that I have defined here. Like when you go from a scalar equation to a parametric curve, it's called parametrizing, or you say you found a parameterization, or the curve is a parametrized curve. There's no actually one way to do that, but in practice, people usually do very common curves the same way. So for example, circles are usually always done this way, at least circles in 2 dimensions, right? So when someone wants to parameterize a circle, we usually use theta to be the parameter. So we call the variable theta, which is an angle. It's really a real number, but it's interpreted as an angle. And if you want to parameterize the circle centered at h comma k with radius r, these are the parametric curves that, this is the parametric curve that is pretty much the standard one used to actually do that. It's important that you realize that it's traversed counterclockwise once for theta going from 0 to 2 pi. Theta going outside this window, like theta going from negative infinity to infinity, for example, you're just retracing the same curve, right? But you go around the curve fully one time on any interval length for theta that is 2 pi long. And so you might actually wonder, why is this the parameterization? It turns out this is the parameterization. X equals r cosine theta plus h, and y equals r sine theta plus k, where theta is allowed to go from 0 to 2 pi, actually sketches out a full circle. And you can actually see this, you know, like given, you know, x minus h squared, y minus k squared equals r squared. What you can do is you can divide both sides by r squared. And what you do now is you realize that, hey, I know a trig identity that looks like this, right? In fact, this now makes it look almost like a unit circle. So what we would do is just make this a cosine. And make this one a sine. And then that equation would be true, right? And this is a trick that we use sometimes. Sometimes we use familiar identities to develop another parametric equation for something, just so that we have something familiar to pin it to that we can always use as a reference. It's always nice. So that would always work. So this would mean your x minus h over r is equal to cosine, which of course would mean your x is equal to r cosine theta plus h. And it would also mean your y minus k over r is equal to sine, which means your y is r sine theta plus k. And so that's where this set of parametric equations come from. Now, one thing you can also notice is that an ellipse would be very similar. So you get an ellipse if the coefficients are different, right? So you get a circle because these r's are the same. The magnitude, the number multiplying the cosine and the number multiplying the sine are the same. You get a circle because you'd stretch the same in the x and y direction. But if you make those numbers different, like x equals a cosine and y equals b sine, where a and b are different, that gives you the equation of an ellipse. That would actually be a parameterization for an ellipse. If your a is bigger, your ellipse stretches horizontally. If your b is bigger, your ellipse stretches vertically. Right, so you could also know something like that. So the parameterization for an ellipse would actually look very similar. Okay, so this is the standard way to do circles, and this is why it works. It's just us, once again, taking advantage of the Pythagorean identities. So this is just something that people know, right? So if they see a set of parametric equations looking like this, they'll know, oh, that's a circle centered at h comma k, right? They'll just know that, and its radius is r. So I could say something like, you know, as an example, I can say x equals 2 cosine theta, y equals 2 sine theta minus 4. Theta goes from 0 to 2 pi. And I won't have to plot points. I wouldn't have to eliminate parameters. I wouldn't have to do any of that. I would just automatically know, oh, this is a circle with radius 2 and center is going to be 0 comma minus 4, right? Like I can just know that just by looking at these parametric equations. So this is what I meant by, you know, eventually you're going to be so familiar with these guys that you're never going to have to go back to like plotting a table, plotting points in a table, or like doing a bunch of substitutions to figure out what's going on. You'll just be able to look at something and know, oh, I know what curve that is, you know. Sort of in the same way when you see like y equals x squared, you don't have to wonder, oh, let me plug in some points. No, you just know that's a problem, right? It's just you look at it and you know. Parametric equations, some of them will be like that as well, or should be like that eventually. You should be able to look at a set of parametric equations and kind of know what the curve, what the picture looks like without going through too much trouble. Sure, to actually plot to actually sketch it in detail, you might have to do a few calculations, but generally speaking, you should have an idea of what the curve is describing. Okay, so this is a very standard way to parameterize a circle. So yeah, so I singled out circles specifically because we're actually going to come back to that when we talk about polar coordinates, and I'm talking about them here again, but I do want to go a little bit more in detail, right? So some standard parameterizations to know: 1 is the circle, 2 is lines. We deal with both separately, but we want to summarize here and talk a little bit more about them. And 3 is almost anything else, where that can get a little bit sophisticated, but essentially it's kind of going to be like another substitution technique that can get you to parameterize various other curves. But there are standard parameterizations for other things as well. It's just that in Calc 2, I can't really tell you. The other standard parameterizations we know are for like 3-dimensional objects. There are some standard ones for a sphere, for example. And so those you will learn when you go to Calc 3. But for now, we're just talking about some standard ones for some basic things like a line or a parabola or a circle. These are the ones I want you to know at this point. Right? So again, once you know something is a circle, for example, you can kind of tweak it to isolate certain parts of the curve because you might not want the entire circle. So for example, let's say I had the full circle. Circle radius 2 centered at the origin. Okay. Then I could do a parameterization here. And I can say, oh, this is just x equals 2 cosine theta. Y equals 2 sine theta. And then I let theta go from 0 to 2 pi. I mean, or like, it depends if I don't care about how many times, or theta going from minus infinity to infinity would work. I would just retrace it an infinite number of times. Right? But the idea is I would be traveling around the circle in this direction. Okay, so as a parameterization. But what if I wanted to do something like the upper semicircle, right? So what if I wanted to do something like this? So it's essentially the same circle. But I only want on top over here. Can anyone take a guess as to what the parameterization would be like for this? Like what would change between the full circle and the upper semicircle?
The upper bound of the parameter would be pi instead of 2 pi.
Right, exactly. You can literally change what part of the curve by varying the parameter. It's kind of like when we were with the straight line, right? Like if I let t goes from 0 to 1, I get this little piece of the line segment, but if I let t go unrestricted, I get the entire line. And again, I could let t go from -1 to 17, and I would get a bigger piece of the line. So I can actually vary how much of the curve I'm traveling around by just varying the parameter itself. So this I could say, oh, it's x equals 2 cosine theta, y equals 2 sine theta. And my theta, I just force it to go from 0 to pi and stop there. Right? And that would still go in this direction. Right. So again, if you were to see this set of equations, you should interpret that as a semicircle without doing too much work, right? You should just realize, oh, that's a circle, and they're just varying the angle we're ranging through. So it's just 0 to pi instead. What if I wanted the, and you can do this for all parts of the circle, like the quarter circle. Say the second quadrant. Okay, so I can do like this part. So this would be -2, this would be 2. And I can say the parameterization here would be x equals 2 cosine theta. That's not going to change. Y equals 2 sine theta. That's not going to change. But let's let theta this time go from pi over 2 to pi. Right? And that would parameterize that circle. Or I could go to something like the right half of the circle. You can talk about parameterizing some of those like this. So, x equals 2 cosine theta, y equals 2 sine theta. That parameterizes this curve going from, I see here, +2. What would the limits on theta be in this case?
Negative pi over 2 to pi over 2.
Right? Negative pi over 2 to pi over 2. By the way, there's a common mistake that students make here. So I should just probably mention it, common mistake. Is saying that theta would go from like, a lot of students have the bottom half, the lower the lower y-axis as memorized as 3 pi over 2. So they might say we go from 3 pi over 2 to pi over 2. But the thing is, it's not increasing. Right. So it doesn't actually make sense to say something that is 3 pi over 2. 3 pi over 2 is actually greater than or equal to pi over 2. So you're actually mixing up directions like that. 3 pi over 2 to pi over 2 would actually look very different. And if you wanted to force that the initial, you can do this, by the way. You can force that the initial is 3 pi over 2 and the final is pi over 2. Although we don't want to worry too much about that in Calc 2, but you could actually force this to happen. And it will have certain consequences for all your integration, all the calculus you're going to be doing. But essentially, that would look like going the other way. Like if you start at the 3 pi over 2 and then go back to the pi over 2. So you want to think of these as initial point and final point. It's kind of important that you think about it that way. It's like you mentioned the initial here, you mentioned the final here.
Would that
So
be
pi
like,
over 2. What?
sorry, would that be like negating a definite integral to reverse the direction?
Yes. Yes. There's gonna be points where you actually want to like integrate over a parametric curve or something like that. And so the initial point will usually be the lower bound on the integral and the final point will be the upper bound. And so you can actually switch these two, and we actually know that the integral from a to b of something is negative the integral from b to a of something. So if you, depending on how you set up your initial and final points, you might have to change things with a negative sign or do something else that you have to be aware of. But yeah, so you want to be sure that you're writing things down in the correct direction and that you're increasing in the right way, because you might actually get something that you don't want. So you could actually try to get, you could try to get the, you might want the right half of the circle, but then ending up with the left half because you chose the wrong limits on your parameter, and you don't want to do that. And it's actually a common mistake. So don't just go based on some picture that you memorized to remember the special trig angles for the values of the trig function at special angles. You want to purposefully choose the initial and final points to get what you want done, actually done. And it can actually make a difference in like the picture of something. I actually want to show you another way to do this. Another way to parameterize the upper semicircle. Okay. And it's kind of, it's sort of using the third method I'm going to be talking about, using the third method we'll discuss. All right, so I haven't really discussed this yet, but it's not a crazy idea. I can actually do it on the fly, and it shouldn't get you lost too much, if at all. Is to, let's say we wanted to start off with the actual scalar equation, like x squared plus y squared equals 4. I know that's the equation of this thing that we've been messing with all the time. In this case, this one went from here to here. Here's something that I could do. I could solve for y. So I get y equals plus or minus the square root of 4 minus x squared. But of course, for the upper, I would take the positive. So I look at y as the square root of 4 minus x squared, and that's actually the equation of a semicircle. And what I could do here is set x equals, say, t. This would mean that my y is equal to the square root of 4 minus t squared. These are parameters. And then I can let my t go from -2 to 2, for example. Now that would actually it creates the upper semicircle. Parametrized in terms of x, right? Now notice what happens here. Because my t is the x coordinate, when x is -2, that means that this would be the initial point. This would be the final point. So I'm actually traveling along this upper semicircle in a clockwise fashion. Now, if I wanted to change directions, I could do that. As we sort of seen earlier, what will actually happen, you can actually negate things. So to change direction, there are actually a bunch of ways you can do it. But I could say set x equals -t and y equals the square root of 4 minus t squared. And that would actually give me that semicircle going the other way. Right? So you can actually change directions by making subtle changes, either to how your parameter behaves. Like you could either force the formality of saying, yes, I know 2 is bigger than -2, but I want to start at the +2 and end at the -2. Or if that might seem strange to you, you can just say, you know what, let's just negate one of the coordinates so we switch the direction. And you can actually do that. You can change the direction by negating. That's an idea that you're going to explore a lot more in Calc 3, maybe Calc 4. Maybe Calc 4 is where you're going to see that more. So that might be a Calc 4 direction. Like you're going to do vector calculus, and direction orientation is going to be super important at that point. And you're going to learn all these little tricks to change directions on a curve and do stuff like that. But negation can actually change the direction on a curve if you know how to apply it. So depending on what you want to create, you can change the direction of that curve. And I also want you to notice that this is a different parameterization for exactly the same thing that we parameterize here. So here I can parameterize in terms of sines and cosines, trig functions, but here I parameterize the same thing, no trig functions, right? This sort of also shows that parameterizations aren't unique. I just gave you 2 different parameterizations for the same thing, right? Right, so like so me saying x equals r so me saying x equals 2 cosine theta, y equals 2 sine theta, and theta goes between 0 and pi, it's the same curve as me saying x equals -t, y equals the square root of 4 minus t squared, and t goes between -2 and 2, right? So I can write down the same curve in very different ways, right? And I don't just mean some simple, oh, I can mold this algebraically to look like that kind of way. I mean, using completely different classes of functions, right? I can describe it in terms of trig functions, and I can describe it in terms of non-trig functions, right? Like I can, 2 completely different kind of parameterizations, and I can tweak each of these individually, right? Like I could make this into t minus 1 and that t into t minus 1, and then change the bounds here, and I get a different parameterization. Like you can do it, whatever is actually most convenient to the thing. Can't go back. Yeah, right. So there are times where you might want to change your parameterization to fit the kind of situation you're in for various reasons. There are times when you might want a trig function, times when you might not want a trig function, or whatever reason. The point is, you can parameterize things in multiple ways. So when I'm showing you here ways to parameterize things, I don't want to, like a circle, I don't want you to get the idea that, oh, this is the only way to do it, right? There are multiple ways to do it. Like there is no such thing as a unique parameterization, but there are just some that they've you know, withstood the test of time. They're simple enough and memorable enough for most people to use it and most people to think of it this way, but you don't have to think of it that way. So this is a very standard, common way to parameterize a circle. It is not the only way. And that's something that I also wanted to point out. Lines and line segments. Once again, this isn't the only way to parameterize a line or a line segment, but it is one of the simplest ways. And in Calc 3, you'll learn the formula for actually doing this in terms of vectors, but I've taken out the vectors out of this formula and wrote them in more scalar equations. So you can actually parameterize a line segment that goes from one coordinate to another coordinate. So you're starting here at the initial point, x1, y1, and you want to go to the final point, x2, y2. You can actually parameterize that by this formula right here, right? So your x1, y1, and your x1, y1, and your x2, y2, these are coordinates. So these will be actually constants, numbers. And so your x and y are just the variables. T is the parameter. And for this formula, it is always t goes from 0 to 1, right? So for this formula, it's always t goes from 0 to 1. But you can parameterize a line in another way, and the limits on t can change, right? But whenever you use this way of constructing a line or a line segment, you always set t lower value is 0, upper value is 1. Because what you'll notice is that, look at these equations. If you plug in t equals 0, notice your x would equal to x1 and your y would equal to y1. So you start at x1, y1. What would happen if I plug in t equals 1? Then you'd have x1 plus x2 minus x1. The x1s would cancel, so your x would equal to x2. Similarly, your y would equal to y2. And so when t equals 1, you end up at x2 comma y2. And so by making t equals 0 to 1 in this formula, you actually get from one point, the initial point that you want, to the final point that you want, just by making t goes from 0 to 1. So this is a very useful trick. There's also, to not even think about it in terms of formulas, there's an important idea that I always think about it this way. And it's just, think of this part here, the part that gets multiplied by the t, as the difference between within each coordinate from the initial to the final. And so what you can do, be careful. What you can do here is you can think of x as starting at x1, then you figure out, what do I need to add or subtract to get to the x2 value? And that is the number that is going to be equal in magnitude to x2 minus x1, and then you multiply by a t. We're actually going to do this. We're actually going to do some examples in a little bit, so you'll see what I'm talking about. But this, of course, this will actually get you like a line. This will actually get you a line segment where you start at x1 comma y1, and then you end up at x2 comma y2, and it can go in either direction. Just depends on how you label the points. If you plug in you just want the x1 and y1 to represent where you want to start, the x2, y2 to represent where you want to end, and you'll actually get a line segment from this formula. It also works in multiple dimensions, so I give you a 3-dimensional example here. So this will actually take you from, so this is the x, this is the y, this is the z. So we're in 3 space. And you can have a coordinate in space here, x1, y1, z1, and then this formula will take you in a straight line fashion to another coordinate in 3 space, x2, y2, z2. And it's this formula. It looks very similar to the previous one. You just extend it with a third variable. Put in a z1, z2, make it look just like the x1, and y1 and the x2 and y2. And yeah, that will actually work. You can, of course, get the entire line that passes through these points by just letting your t go from -infinity to infinity. And that would also work. So for this, you can get like an entire line going on that passes through like your x1, y1, and your x2, y2. But if you were to force the t to go between 0 and 1, you would get this part. And your t greater than 1 would give you over here. Your t less than 0 would give you over here. Right. And so this would be like the main line segment for t goes between 0 and 1. But if you let t get unrestricted, it just keeps going, and it won't stop in these equations. Like the x coordinate can keep getting bigger, the y coordinate can keep getting bigger, and you keep moving. So let's actually look at some examples using these formulas. Now you could memorize these formulas, but I think there's a very intuitive way to think about it, so you don't really have to remember the formulas. So let's say we wanted to parameterize the line segment, this one. Okay, so I have a line going from 1, -2. And it's going all the way up to 3, 4. Obviously, I'm thinking about it as going in this direction. Okay, so this is 1, -2 going to 3, 4. Now, what would a parametric set of equations look like for this? And again, there is no unique way to do this. I'm just going to give you a way to do this, right? Specifically, the way based on what these formulas are trying to tell us. So here's how you think about the x coordinate. So you know your x, your y is going to be something, and your t is going to be from 0 to 1, because I'm using this way of writing things down. So here's how you think about it. So you look at the x coordinate, right? Just let's focus on the x for a second. Where do we want it to start? Well, obviously at 1, so you write down 1. Now here's what you think, right? So start with x equals 1. Think, what do I need to add, subtract to get to x equals, what's the final point? 3. Right? That's what you think. Now, to go from 1 to 3, what do you need to do? You need to add 2. 1 plus 2 would give me 3. So you go plus 2. And then you just attach t to that number. Similar for y. So you just put a t on that part. Same thing for y. Y starts at -2. So I write down -2. I want it to end at 4. So I think, what do I have to add or subtract from -2 to get to 4? Well, if I take -2 plus 6, that will give me 4. So then I take plus 6t. And that's the parameterization. So this is a way to parameterize this specific line segment. You can give me 2 coordinates, and I could straight away write down a parametric set of equations that describe to you that line segment. And give another example. Say parameterize, just in case you're still writing down, parameterize the line segment from say 1, 2, 3 to -4 to 0. Okay, so this is again, it's a line segment, it's a straight line, but it's obviously in 3 dimensions. So we know we're going to have an X, a Y, and a Z, and we're going to have our T, which in this formulation is going to be between 0 and 1. So what is the X? You start with a 1. And you think, what do I need to add or subtract to get -4? Well, I need to subtract 5. So I'm going -5t. That's it. Then you start with a 2. What do I need to add or subtract to get to a 2? Well, you need to add 0. Right? So which you wouldn't write that down. You just say y equals 2 all the time, because y does equal 2. It's constantly 2 on this line. Then you ask the question, well, my z starts at 3. What do I need to do to get to 0? Well, I need to subtract 3 and I attach a t to that. And that is the parameterization of this line segment. Now, don't worry that you don't know how to graph this line at this point. That's not the point. The point is to just know how to parameterize the line segment. You'll learn how to graph 3D stuff in the next class, for those of you who need to go on to it. But the idea of knowing what a parametric curve is, how to get a parameterized curve for a specific kind of equation, is something you should need to know how to do. So parameterizing lines and circles is something you're going to be doing, you'll need to do all the time in practice. So knowing how to do them is very important. So we looked at how to parameterize circles. We looked at how to parameterize lines. We understand that parameterizations are not unique. It's not the only way to do things, but these are the popular way to do things. Like it's the standard way to do it, right? Most people, unless they have a very good reason to do it some other way, would do them this way. So the third technique I want to show you is parameterize almost anything else. It can work in a variety of scenarios. And I actually showed you earlier how to do this with parameterizing the circle another way. So this could parameterize a cubic, a quadratic, something else. If you want to, for example, we looked at hyperbolic trig functions. So that should also give you the idea that if you wanted to parameterize a hyperbola, for example, that you would use the hyperbolic cosine and sine in that endeavor. But that is, things like that would come up. But let's say you're doing like for almost anything else. So let's say I wanted to parameterize the parabola, right? Or a part of a parabola. Let's say I want to parameterize the part of y equals x squared, but I want to just do it from the origin to the point 2, 4, right? So I have, right? So there's the curve y equals x squared. But I really only care about going from here, the origin, and moving up to two, 4. Okay, so I only want to parameterize that part of the curve. So this involves, I think I typed it out here. Right. So you make one of your variables the parameter. So for example, in this case, notice that I made x the parameter. I said x was t. By the way, don't get weirded out, but people, you could say something like x equals x. Sometimes people get weirded out by that. Equivalently, you could say set x equals x, then your y would just stay as 4 minus x squared, and then you let x go from -2 to 2. That would be an equivalent set of things. So sometimes people just, if they know they're going to set a variable to be a parameter, they just call it itself, and you can still do that. But sometimes to emphasize that we're switching parameters, people just want to call it by some other name, like a t or something like that. And so that's the idea. So sometimes you have a curve, looks complicated. What you can do is you can parameterize it in terms of the input variable of that curve. And this is an idea that actually extends to multiple dimensions. So if you have a curve with 2 input variables in it, you can let one input variable be one parameter, the second input variable be another parameter, and the third output variable is just a function of those 2 parameters. So in a similar way here, you can set x equals t, and then that would just mean y equals t squared. And since x is t, your t would follow the x coordinate. So it would go from 0 to 2, right? T equals x. So the x limits give the t limits. Okay. And that would be the parameterization for the parabola. By the way, should note again, it's not unique. So alternatively, I could let y equals t. And then this would mean I can set x equals to be the square root of t. And then let t go from 0 to 4. That would trace out exactly the same curve. In exactly the same direction. Okay. So I can let x be the parameter, solve for y in terms of x, and then run with that. Or I can let y be the parameter, solve for x in terms of y, and run with that. These 2 guys will actually give us the same curve. So I can take the positive square root. Obviously, the negative square root would give me the left side over here, but that's not the side that I want. So technically, yes, x is plus or minus the square root of t, but you just take the plus part because that's the part that you want. You want the right side of this. Right. Yeah, so that is how you can go about. Those are the main things I want to show you about parameterization. So parameterizing circles is something that you should know how to do. We have standardized formulas for that. Parameterizing straight lines, some you should know how to do. We have standardized formulas for that. And if you're in any other case, you should try to get this technique to work. Just pick a coordinate, whichever one is more convenient at the time, and set that equal to a parameter, solve for your other variable in terms of that parameter, and then the limits will follow whatever variable you made be the parameter in the first place. Right? And one can be more convenient than the other. For example, if I wanted to go from -2, 4 all the way up to 2, 4, then this parameterization is clearly a better parameterization to choose. Because looking at it in terms of this way, I would actually need 2 sets of parametric equations. I would need a positive radical t and a minus radical t. And then I'd have to stitch these 2 parameterizations together. It's not very convenient. So things can make a difference based on the context in which you're in. But this is how we'd parameterize curves. This is how we'd sketch parametric curves. This is what parametric curves are. And it's what I need you to know about them at this point. So that's the basics, the definitions, the fundamentals on how to think about them, how to graph them. But this is a calculus course, so we should also know how to do calculus with parametric curves. So, you know, some of you might be wondering, or some of you might not be wondering, some of you might not care, but some of you might be wondering, okay, so let's say all right, I understand parametric curves. Yes, I understand that was the whole idea behind trigonometry, and we have this beautiful subject, trigonometry, now because of this idea, and that's all well and good. But if I have a parametric curve, if you give me just a set of equations that corresponds to some curve, like how do I find a derivative? How do I find a slope? How do I talk about that curve or analyze that curve in calculus, in a calculus context? And it turns out it's actually not that bad. And that's what we are going to look at now. We're going to talk about what would it mean to talk about derivatives in this context. Limits actually won't be too different, right? So you can just say like the limit as t approaches something, and it'll be just like limit as x approaches something. That's not going to be different. What would be different is something like a derivative. Because when you split two coordinates as separate things and you start talking about the slope, well, the slope is considering both together, right? You want to know how one changes with respect to the other. So when you separate the two in two different worlds, how do you talk about the slope that they make up together? And the answer is the chain rule. The chain rule is how you're going to do it. So we're actually going to apply the chain rule, but we're going to apply it in a way that you normally don't actually see it, but it is one of the ways it was defined before. Right. So normally this is equivalent to the usual way like a calculus student would think about the chain rule, is when we say, oh, we want to find the derivative of a composite function. And what we do is you take the derivative of the outer function, leave the inner function alone, multiply by the derivative of the inner function. Right? So it turns out you can actually think of this, obviously, it's the derivative of f and you evaluate it at g, and you plug g into it. So in other words, you can think of this as df dg. And here you can think of this as dg dx. Right? So it turns out derivative notation, the differential notation, Leibniz, bless his heart. So Leibniz and Newton developed calculus independently, but Leibniz's notation was actually more convenient than Newton's notation, because you can get this kind of thing where you can sort of, the notation can kind of cancel as if you're having a real fraction, and you can actually separate these fractions and talk about differentials as their own kind of thing. And you'll get, oh, this is df dx, the derivative of f with respect to x in this case is going to be have this breakdown in multiplication. And it sort of cancels and gives you back something very nice. So that's how we're looking at this here. Turns out dy dx, we can think of y as a function of u and u as a function of x, and then think about dy dx as dy du times du dx. Of course, for us here, the middleman, this intermediate variable like the u, which is when you learned, if you learned the chain rule via substitution, which is a weird way to do it, but your teacher probably had pedagogical reasons for saying it that way. If you learned about it that way, then we're going to sort of do the same thing, but we're using t as the variable now because we can. And so when we look at dy dx, we can just say, oh, this is dy dt times dt dx. And again, it turns out the differential notation, you can actually treat them like fractions. So I can think of this as, when I multiply by dt dx, I can think of this as multiplying by the reciprocal of dx dt. So I can actually think about this like dy dt divided by dx dt. Right? And yeah, it's crazy. You can actually do that. So this is like y prime of t divided by x prime of t. Right? So it's the change in y, and you're measuring its magnitude as a change in x. It's kind of like a dy over dx, you know, your delta y over delta x. And you find the limit as the delta x approaches 0. That was what gave you the derivative. And yeah, a very similar formula ends up being true here conceptually. So it turns out you can actually find the derivative dy dx in terms of the parametric derivatives. And it's by this straightforward formula. Very nice. So yeah, this means you want to find your dy dx. Well, that's just going to be your dy dt divided by your dx dt. If your x is given as a function of t, your y is given as a function of t, and the derivative of the parametric curve. Right, so that's a formula we know. Okay, so if I give you a parametric set of equations, and I want you to find the derivative, just say the derivative of the y formula divided by the derivative of the x formula. That's it. By the way, that's another way we can know that a parametric set of equations with linear terms is also linear. Because if you look at something like, yeah, like sure, let's go back to this example. If I take dy dt, I would get 2. If I take dx dt, I would get -1. Divide those, I would get 2 divided by -1. I would get -2 is dy dx. So with a set of equations like this, the slope is constant. The slope is a constant -2. In fact, that corroborates what we did before. Once we eliminate the parameter, we realize we got a line with slope -2, right? So this is kind of showing you, illustrating that this way of thinking is actually, it actually works. And you can prove that it works in general. So it's not just, oh, we're moving around notations in this weird way. It actually works out to think of it this way. So you figure out how the y is changing with respect to t, figure out the x is changing with respect to t, you divide these. It's equivalent to you finding the derivative in the xy plane. Right. So it's like you're splitting space into 2 parts. One considers x corresponding to this variable t, so there's an xt axis, and then there's another world with the yt axis. But they both can come back together to make the xy axis. And you can talk about the derivative in the xy world by looking at the derivatives individually in that world. So that's how you'd actually find the derivative. And you can actually do a very similar maneuver to find the second derivative. And this formula actually starts getting significantly more complicated. It's not super complicated, but you'd kind of see from this that beyond this, like the third derivative, fourth derivative, fifth derivative, that will get a little bit more complicated with respect to x anyway. So we actually just stop at the second derivative. So we'll know about the slope and we'll know about concavity for parametric equations. We're not going to worry about anything else, but you could go for the second derivative, d squared y dx squared. And remember, the second derivative is just the derivative of the first derivative. And again, it looks like we're doing something like, can you do that? Just play around with notation this way? But you can, and it's interesting that it would work out this way, but Leibniz knew what he was doing when he invented this notation. He went and he's like, okay, see this d dx that I had here? let's just divide each by a dt. It's like, okay, dude. So here you have d dt of dy dx. Divided by dx dt. We can kind of slip this off to the side, but we can multiply it again. Because again, you can think of these derivative notations like fractions. And so what he found was, oh, if you take the derivative with respect to t of the previous derivatives that you had, which is dy dx, and then you divide that again by the derivative of x with respect to t, that's equivalent to you finding the second derivative. So you end up with that. So the second derivative, d squared y dx squared, that is just going to be d dt of the first derivative divided by dx dt. So work this out. If x equals x of t, y equals y of t, and derivative exists. So those are the two formulas. We can find derivatives in this way. And now, before we use them in some examples, and I'm going to tell you some more things like, well, I actually wrote it down here, and I guess you could read it up, leave it up, right? So you might also want to know about things like horizontal or vertical tangent lines. And this kind of corresponds to how you might think about it. You get a horizontal tangent line when dy dx equals 0. But to make that happen, you just need the numerator of this fraction equals 0. So you can set dy dt equals 0, but your dx dt is not 0 at the same time, because otherwise you get a division by 0 that you'd have to worry about. You get a vertical tangent line in the opposite scenario. If your denominator is approaching 0 and your numerator is not 0, then you get a horizontal tangent line, because it means like your y is changing within a 0 horizontal direction move. So that means it's kind of shooting straight up. Or I think you can also think of it straight down, depending on if it's positive or negative. And you get that. There is also the idea, what if both are 0 at the same time? Then at that point, you would have to take a limit, right? Take the limit as t approaches the point that makes dy dt equals 0 divided by dx dt equals 0. You can use L'Hopital's rule and you can figure out the slope that way. So if both are approaching, if the denominator is approaching 0, the top is not, it's undefined. If the top is 0, you get a horizontal tangent line. If the bottom is 0, top is non-zero, you get a vertical tangent line, which again means tangent line is undefined. If both are approaching 0 at the same time, that is an indeterminate form. You cannot evaluate that at face value. So you actually take limits to inch close to that point and see how it behaves. And often L'Hopital's rule would come in handy for that. So those are the main concepts we need to know about the derivatives. And we're actually going to use these to do things like find equations of tangent lines and the same sort of analysis that you did in Calc 1. We can do that again, but now we're going to do it in a parametric equations context after the break. So we'll take another 5-minute break here, and I will see you guys in a little bit. All right, so now we know the formulas for taking derivatives and how to find some interesting properties of the tangent line. Cool, let's move on. So this is the first example we're going to do. By the way, that's a very interesting function. The x is a quadratic, the y is a cubic. Like, what would that even look like? Like, I mean, technically you could solve for the t, right? And you could be like, oh, t is equal to, well, first you'd have to write this as like t squared minus t plus 2 minus x equals 0. And then you can do like a quadratic formula kind of thing. And you'd be like, oh, it's minus b plus or minus the square root of b squared minus 4 times a times c all over 2a. And so then your y value would look like that guy cubed. This is not a t, this is a 1. Then your y value would look like 1 plus or minus the radical of 4. So that's x minus 7. 4x minus 7 over 2 cubed minus 3 times 1 plus or minus the radical of 4x minus 7 over 2. Like, imagine having to graph that guy. It's really messy. So, I mean, even if you eliminate the parameter, like graphing this is going to be a nightmare. And plotting points, it'll also be a nightmare. I mean, you can tell from the formula that I just gave you. But this one, it turns out, isn't even a function. And a part of that is because of the plus or minus. But a part of, yes, a part of that is because of the plus or minus. I guess that's the main reason. So this is actually not something that looks very nice. I actually put a picture of the graph here. Now, I didn't ask you to graph it. And that would be very unfair of me to ask you to graph it. Like it'll take you forever to graph this thing, but it's just showing you the kinds of things that like you might think like, okay, parametric equation just seems like we're just making something more complicated than it wants to be. But honestly, I'd rather deal with a quadratic and a cubic than deal with that huge monstrosity that I would have had if there was no t to think of this in terms of. It's much easier to just break things down into simpler parts first and deal with that. But this is the original curve that we want to examine. But obviously, this curve is very complicated. However, we can break it up into a way that the x-coordinate behaves like a quadratic and the y-coordinate behaves like a cubic. But we might want to still be able to do something like, what if I want to find the equation of a tangent line at this point? How would I do that, right? So I might still want to examine this curve with calculus. So that's what these questions are asking about. How would I find the slope? What is dy dx? What is the second derivative? What if I care about concavity along this curve, right? What if I want to find where the tangent line is horizontal or vertical, right? So a tangent line, we'd have a vertical tangent line, obviously, like at some point in the curve, there's a vertical tangent line. There's like a horizontal tangent line here. There's another one right here, right? So I expect to find like 2 horizontal tangent lines. There's probably a vertical tangent line somewhere else. Depends on what the curve is doing as you go off to infinity, but it doesn't seem like that. Seems like there's only 1 vertical tangent line. What if I wanted to find the locations of all these tangent lines, etc.? When is the slope 3? So at what point would I have like at what point would I have a tangent line where the slope is 3? Right? Or what is the tangent line when t equals -2, right? So that's kind of like asking me about a certain coordinate. What is the slope at this point, right? And of course here, it's easier for me to think in terms of t's than it is in terms of x's and y's. And so I might want to describe a point in terms of the t. And that's going to be something that's it's a general application. Like another reason why parametric equations are important is, and why we use t, it's kind of like a physics background. Like t stands for time usually, and sometimes we want to, think of positions on x and y in terms of time. And so we might want to say, when time is 5 seconds, what's going on? What is our rate of change? What is our position? What is blah, 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 right? But this is a sort of question that we can ask. So this is the kind of thing that I could ask you, a very common type of problem with parametric equations. So I can ask you to identify parametric equations. I can ask you to sketch parametric equations or identify sketches based on parametric equations, parameterize things in various different ways, parameterize various kinds of functions. But I could also directly ask you some calculus questions. I can give you a parametric curve and say, what is the derivative? what is the tangent line at this point? Where is the tangent line horizontal? And I expect you to be able to do that. So let's actually jump in and actually do that. So it turns out we can do this based on these formulas. Right? So let's find dy dx. And we have our x and y right here. Right? So yeah, let's actually do that. We know that dy dx, we have a formula for that. It was y prime of t over x prime of t. So in this case, our dy dx in terms of t is actually going to be, take the derivative of the y, 3t squared minus 3, divide by the derivative of the x, 2t minus 1. And we're done. That's it. So that is the slope in terms of our parameter t. Right. Very nice. I think the formula is a bit weird, but let's move that a little closer. Okay, now what about the second derivative? Well, we have a formula for that too. We know that d squared y dx squared is equal to the derivative with respect to t of the first derivative divided by the derivative of the x with respect to t. So this means I want the derivative with respect to t of the first derivative, which is this 3t squared minus 3, over 2t minus 1. So I'm going to find the derivative of that and divide by 2t minus 1, which is the derivative of the x. So now I'm just going to compute those derivatives. So obviously for the top one, I'm going to use like the quotient rule, and then I just divide that answer by 2t minus 1. So it's the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared all over 2t minus 1. So obviously the denominator will now be 2t minus 1 cubed. And the numerator, let's multiply that out. That'll be 12t squared minus 6t minus 6t squared plus 6. And so that would be here 6t squared minus 6t plus 6. I mean, you can factor out a 6 from that, but I'm not too worried about it. That's our second derivative. Any questions on that so far? It's going to be annoying. Let's say here, find the t value of the points. or tangent line is horizontal, vertical. Like I can find the x and y coordinates by just plugging those x values, plugging those t values into the x and y, but like I don't want to have to go through all that. Pass it and test the expressions might be a little bit easier to evaluate. Let's actually see that. So we know that one horizontal tangent lines this means dy dt equals 0, dx dt not equals 0 at the same time. Now dy dt was 3t squared minus 3. This means t squared equals 1. This means t equals plus or minus 1. And you just make a note here, note dx dt not equal to 0 for these t values. If it was 0, that would be an issue. You can also note, which I'm not going to do here, also note if asked for the points or x, y coordinates, we would plug these t values into the parametric equations. So one would be the x evaluated at 1, the y evaluated at 1, and the other one would be the x evaluated at -1, y evaluated at -1. And those coordinates would give us the horizontal tangent lines. And that actually makes sense. We kind of see from this picture that you expect to be 2. So it turns out for one of these, your t was -1. For one of these, your t is actually 1. And it corresponds to those points. So we see that there are 2 places where there were horizontal tangent lines here. They correspond to when your t value equals plus and minus 1. Now, for vertical, this means your dx dt equals 0, your dy dt not equal 0. If both are 0, you have a 0 over 0 situation, and you can't just make a conclusion from that. You have to do like take limits as your top and bottom is approaching 0 and do like a L'Hopital's rule or something like that. But here they're not actually 0 at the same time, so we don't really have to worry about it. Here, your dx dt is 2t minus 1. So this is t equals 1/2. So you'll notice there's only one spot where we have a vertical tangent line, and we can kind of see from the picture here as well. There, you know that part here is where we have like a vertical tangent line. There's nowhere else where this curve looks like there's a vertical tangent line, and the calculations kind of bear this out. Yeah. And again, if I wanted to find the coordinates, I would just plug in t equals 1/2 into the quadratic here, and I would get the x coordinate, plug in t equals 1/2 into the y, into the cubic here, and I would get the y coordinate. But here I'm just asking for the t values of the points. So those are them. Any questions on that? So I can also, what was the third question? I think it's down here. Yeah. When is the slope 3? Right. So again, here we're asking when is dy dx equal to 3? Oh, so, but we know what that is. This means that 3t squared minus 3 over 2t minus 1 equals 3. Is that 3t squared minus 3? Let me just double check that one. 3t squared minus 3, 2t minus 1. Okay. So that's it. So now we're just solving this equation. So this is 3t squared minus 3 equals 6t minus 3. Of course, this can add 3 to both sides. That kills that. And so here, this just means 3t squared minus 6t equals 0. Can factor out a 3t. So you can get when t equals 0 or t equals 2. So at those times, our slope would be equal to positive 3. So there will be at 2 points, our slope is equal to positive 3. Oh. And then this is probably borne out in the graphs. So it's like, I'm just randomly guessing here. So somewhere like there and somewhere like here, slope would be positive 3 at these 2 points, something like that. Okay. Now let's bring it back to Calc 1. Back to the days of finding the equation of tangent lines. PTSD of doing that. Well, maybe not. That was so bad in Calc 1, right? I'm guessing. But here we want to find the equation of the tangent line when t equals minus 2. Right? So ultimately we want like y equals mx plus b, but it must be when t equals minus 2. So we know for a line, what we need is we need a slope and a point. So first, find slope. So this means we want dy dt when t equals minus 2. This means we want 3t squared minus 3 over 2t minus 1 when t equals minus 2. This means we're going to plug in minus 2, minus 2. So that is going to give us 2 4s 8, minus 3 5, divided by minus 5. So we get minus 1. So that's our slope. This is our m. Second, so that's the slope of the tangent line. Now we need to find the coordinate that the line passes through. Of course, we know the point. This is when t equals minus 2. When t equals minus 2, this means your x would be, go back to what the x value was, t squared minus t plus 2. This is 4 plus 2 plus 2. So this is 8. And our y so it was t squared minus t plus 2, and then t cubed minus 3t. Our y is t cubed minus 3t. So that's going to be minus 8 plus 6. So this means the point is 8 comma minus 2, which I'm going to call x1, y1. And then now we know by the point slope form put it up here. We know that our y minus y1 equals m x minus x1. So this means that y minus the minus 2 gives me m. M in this case was minus 1 minus x1, which is 8. So that's the equation of the tangent line. Or some students have the compulsion to write this as my mx plus b even when they're not asked, but the first thing here is a bona fide equation of a line. But if you wanted to write it in the other form, it's going to be minus x plus 8 minus 2. So that's y minus x plus 6. Okay, so finding the tangent line, the same game as Calc 1, right? You have to find the slope and a point. The slope is given by the derivative evaluated at the point that you care about. That is what creates a tangent line. So that's all we did. We found what the value of the derivative is at the point we care about. We know the expression for the derivative. So we plug in the point that we care about. The slope was minus 1. Then we find the coordinates by computing the x and y based on the time we care about. And then we just plug this into the point slope form. So any questions on any of this? On any of these problems, like finding the slope, finding the second derivative, finding where a tangent line is horizontal or vertical, finding where a slope is a specific value, or finding the equation of the tangent line at a specific value? Is that all clear? So the subject matter is elementary. It's more Calc. We're really going over Calc 1 stuff. It's just in a different context. And in the end, I think if you know these formulas, you'd be okay, right? It's just that now to you, when you're in a parametric context, this is what the formulas for the slope are, and the second derivative and so on. And again, I could ask you, oh, where is the curve concave up, for example? And what you would do is you just set the second derivative greater than or greater than 0, right? And then that would just be the top part being positive, and you can solve for t. You'll have a range of t for which that's true. So it'll be up to some point, and then after some other point up to the other point, because you see that this is just a parabola and the two ends are going to be positive. So it's going to be concave down in the middle interval and it's concave up otherwise, but yeah, sure. But yeah, all the concepts other than us dealing with these specific formulas, they're just like back in Calc 1. So nothing else here. We're just learning a different way to look at functions, namely through a parametric view of functions. And it's just looking at our functions in terms of what their individual coordinates are doing, not as what a general formula. So in terms of thinking of things as x and y, you think about, what if I think of the x and y separately as doing their own thing, and I'm measuring them individually by their own functions? We end up with what's called a parametric curve or a parametric set of equations. And now we're just kind of learning about, well, how do we sketch things in this kind of view? How do we find derivatives under this kind of view? And so on, right? So that's all we're really doing. Yeah. So here is something else we'd want to be able to do in the parametric world, finding lengths and distances. So we are going to cover something that's covered a little bit in, I want to say section 10.2, but there's a part of this that's also covered in section 8.1, which so we're actually going to do both of those parts at the same time, because they fall in line with each other very well. So you see there's arc length in 8.1, but arc length in the parametric context is also discussed in 10.2. And so we're going to do both arc lengths at the same time. So in 8.1, you didn't know about parametric equations. So there is a version of arc length which doesn't look at parametric equations at all, but we can derive one from the other pretty easily. So I'm going to derive what arc length is in the parametric view, and then I'm going to show you what an equivalent formulation is if we just stick to the XY world. And but basically the idea is we want to find the length of a curve between a specific two specific points. So let's say I had this curve here. So here's a curve. It's a parametric curve given by x equals x of t, y equals y of t. Let's say it goes from t from between a and b, right? So let's say here's the first point. No, so this is the coordinate x of a comma y of a, and let's say it's this point. So this is x evaluated at b comma y evaluated at b. And I actually want to find what is the length of the curve. So here we want the length of the curve from xa, ya to xb, yb, right? Like what is, if you were to walk along this curve, how far would you have to walk to get from one point to the other, right? That's the kind of question that we want to ask here. This is called arc length. And I think there's a space there because it's two words, arc length. Right, it's like the length of an arc, okay? Which is just a path along some curve. You want to find out how long do you have to travel from here to there. So by the way, this is equivalent here. The way I'm going to set it up, I'm going to again, just like in Calc 1, we're going to split things up into subintervals. So I can say this is like T0 and this is like T n, or here, I'm just going to do a few like T4 or maybe even T3. I don't need to go that many to explain to you the concept, right? So let's say I create some line segments, like boom, 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 right? Where this occurs at T1, this occurs at T2. Okay. So here's the idea. I'm going to approximate the length of this curve by the sum of the lengths of these line segments. Kind of like how we approximate the area under a curve by the area of the rectangles that we can form under the curve. And obviously, the idea is the more line segments I use, the closer I get to the actual length of the curve, right? And the idea is if I use an infinite number of line segments, right? Like just a line segment to go from one point to the next point, then we would get the exact length of the curve, right? So we're taking this calculus idea. That's one of the main ideas from calculus, by the way. If you were to like the essence of what calculus is telling us is to one of the things that it teaches us is to break problems down to smaller things and look at the aggregate, look at the infinitesimal. And then once you know how to deal with things in small chunks, then if you create an infinite number of these chunks on the aggregate, they'll give you what you want, right? So it's a very kind of strange statistical view, I guess. So this would be this would correspond to x at t0, y at t0. Here, this would be x evaluated at t1, y evaluated at t1. This here would be x evaluated at t2, y evaluated at t2, and so on, right? So I use 3 line segments, but I can use many more line segments and get a more accurate approximation for the length of the curve, right? And so we're going to use this idea to kind of figure out how do we find the length of this curve between those 2 points. And the idea is I'm going to figure out how I can do it for these 3 line segments. And then what I'm going to do is I'm going to let the number of line segments approach infinity. And so we won't have any gaps here. You'd be able to zoom in and just have these little line segments just going along the curve. And that will give us the exact area, the exact length of the curve. Okay, so here's the derivation. It's actually not as bad as you would think. So you'd say the sum of the lengths of the line segments approximate the length of the curve. And the more line segments we use, the better the approximation. And infinite line segments, infinite number of line segments will give the exact answer. Right. And so that is the calculus idea, right? That's what calculus is about, right? How do you actually formalize? What does it mean to have an infinite number of line segments? And so that the whole point of doing that was to figure out the limit, right? So that's a limit helps us do that. So it's like you're taking the limit as these subintervals, the length approaches 0. And so we needed a concept for what does it mean to actually approach something. And so that created the limit, and that's where the study of calculus began, and everything kind of built it up from there. Like calculus is really like the study of limits, right? The derivative is a limit and the integral is also a limit. But this idea of breaking things up into small pieces and then taking a limit as those pieces approach a certain kind of thing and getting an answer from that is kind of what calculus is all about. At least differential calculus kind of thinks of things that way. And integral calculus in some sense as well. But that's the idea. So I can actually do that here. So the length of if I look at the length of the red curve, well, what is that going to be equal to? Well, I could just take the length of these line segments, right? I can just say, oh, this is the square root of x of t1 minus x of t0 squared plus y of t1 minus y of t0 squared. All right, so that's like the length of the first line segment. And like, I'm going to do the notation, call this like x1, call that x2, etc. Like, and this, call this like y1, and call this like, sorry, y0. Right, so plus, you can do this. This would be like x2 minus x1 squared plus y2 minus y1 squared. And clearly you can continue this idea. You can continue like n times, like xn minus 1 squared plus yn minus 1 squared, and we can get to the final one, right? In other words, you can think of this as like a sum, where, I goes from 0 to n, and what you're measuring is a radical, and you're measuring kind of a change in x squared, right? The distance between the x value, the final x minus the initial x, that's like a change in x, plus a change in y, right? And so the exact length, the length of the curve, it's just taking a limit as n approaches infinity of this guy. Okay, so you take the limit of this, and if this starts to look like a Riemann sums, obviously that's where we're going. So I don't know if you figured that out, but we can actually transform this into a Riemann sum. And because we want to do this for parametric equations, we're going to do this in terms of t. So what I can do is here, I can multiply this by delta t over delta t, and then take the bottom one and bring it inside the radical. So then this would look like delta x over delta t squared plus delta y over delta t squared times delta t. So this is like your f of x times dx sort of thing, except here we're doing our in terms of t's. And this is a bona fide Riemann sum. And now we see a geometrical interpretation of an integral that's actually not an area. This would give you an integral. Say x prime of t squared plus y prime of t squared. Because we know that delta x goes to dx, delta y goes to dy, dt, right? And this is obviously t goes from a to b. And so we can get this integral in terms of t, and the interpretation of this integral is actually a length, right? It's not like an area integral. The interpretation of this integral in this formula gives you a length. And that ends up giving you this. So the shorthand version of this formula is this one that I just wrote down here. So if you have a parametric curve, x equals x of t, y equals y of t, t goes from a to b, and the derivatives are actually continuous on the interval a, b, then as the curve is traversed once, as t goes from a to b, this formula actually gives you the length of that curve. Integrate from a to b of this expression, and that will give you the length of the curve. So I did all of that to derive this. This is what you want to remember, right? That formula gives you the length of a parametric curve as t goes from a to b, assuming that this traces out the curve once, and you don't go like a back and forth, right? If you go like a back and forth and trace the curve multiple times, you'd want to restrict your t a little bit more, right? So just give the minimum window of t that would trace along the curve one time, that will give you the length. So let's find the length of this curve, right? Suppose I give you this parametric equation. X is actually an exponential, or it's kind of like double a cosh function. So x is like 2 cosh t, but we can write that in terms of exponential, e to the t plus e to the minus t, and y is actually linear, and t goes from 0 to 3. This curve looks like this. And it's just like this arc right here, and it kind of grows exponentially going in one direction. So we're actually going to find the length of this blue curve. Okay. And we have the parametric equations of that curve. So this is another problem type I could ask you. I could give you a parametric curve. And I can say, you know, give you a limits on that curve. And I say, how long is this curve? Find the arc length of this curve. Find the length of this curve from this point to that point. Tell me what is the distance you would have to travel to move from one part to the other part. And it turns out there's a nice integral formula that does that. So this is another application of integration. So by above. We know that the length is going to be given by the integral from a to b of the square root of x prime of t squared plus y prime of t squared dt. In this case, our a, right? So this is like the a and this is like the b. So in this case, the integral goes from 0 to 3. Then I'm going to take the derivative of x. Derivative of e to the t is e to the t. Derivative of e to the minus t is minus e to the minus t. Plus, and I'm going to square that and take the derivative of the y squared. Let's go over here. Derivative of the y squared. Derivative of y from this is minus 2. I'm going to plug that in here. We're going to square that. So I can square this. If I square the first one, I would get e to the 2t minus 2 plus e to the minus 2t. And I square the second one, I would get 4. Now, if I add these two, I would get e to the 2t plus 2 plus e to the minus 2t. And so now I have to actually integrate this expression, which at this point might seem like, well, how would you integrate that? What rule would we use? But the trick here is actually strategy 2. Turns out that you can rewrite this algebraically, simplify this to write it a nice way. And the idea would be to compare this with this part. Notice that these two things look the same, except the middle sign is different. And where did this one on the second line come from? Well, it came from a perfect square here. So I take a perfect square with a negative middle sign, I get this guy. What would I get to have a positive middle sign? I can also think of it as a perfect square, just make the middle sign positive. So it turns out that this is just actually e to the t plus e to the minus t all squared. This is, of course, got to be careful here. This is absolute value of e to the t plus e to the minus t. In this case, the inside is positive, so we can ignore, because it's two exponentials. An exponential is always greater than 0, right? E to the t. Inside is positive. So we can ignore absolute values. If it was possible for the inside to be negative, then of course, you'd have to split it in two and take the negative integral of one of them. I think you've done that in Calc 1, so we're not going to worry about it right now. But technically, the square root of something squared gives you the absolute value. In this case, the inside is positive, so we can ignore the absolute values. So we're really differentiating, we're really integrating this guy. Integral of e to the t is e to the t, integral of e to the minus t is minus e to the minus t between 0 and 3. So we're going to plug in 3 minus plug in 0. And so that's just this length. E cubed plus 1 over e cubed minus 1 over e cubed is the length of this curve. So I want you to try this. I'm going to derive this for you next time, but at this point I can actually just tell you this is what we're going to cover next time, or the beginning of what we're going to cover next time. We're going to cover a bunch of things. And I actually want you to try these examples. I actually gave you the answers here so you can check your work. But going back to like 8.1, this is the formula for arc length in X and Y. You can actually write it in terms of the first derivative in terms of X and Y. And this is the formula. So try to apply that formula with these problems here. And we'll start next class like that. So this I expect you to know, but we'll actually do the derivation next time. You don't need to know how to derive it, but we're going to do it anyway. But for now, we will stop there. 9 on the dot, so I will let you guys go. Have a good weekend. Have a good night. Hope everything was clear. Any concerns or questions, you guys can email me, but it's late, so I'll let you guys go, and I'll see you guys in the next one. Ciao.